Hello there. In this video, we are going to go through another example with the QPython package where we are going to set a maximum capacity of the whole system. So in an earlier video, we looked at setting a maximum capacity for each of the different nodes in our queuing network. This video is about setting a system-wide restriction on the number of customers or whatever flows through your network at any time. So let's start at the top of this little code example. Is that too big? Maybe that's good right there. And of course, we import the QPython package. And as we've seen many times before, we define a network model that involves arrival distributions. So in this case, we have two arrival processes because we have two nodes in this system. And they each, in this case, have exponential distributions, one with a rate of 2 at the first node and one with a rate of 1 at the second node. And then for the service time distributions, the amounts of time it takes to complete whatever the service is, whatever the node does as work, or what a server at a node does for work, follows this distribution. So in this case, we've got rates of 1 at both nodes. Great. In terms of routing, in terms of suppose you're starting at one of the nodes in the system already, and then you complete your service there, what node do you go to next? If you're at the first node, there's a 50-50 chance of either going to the second node or leaving the system entirely. And if you're at the second node, you don't go back to the first, 100% chance that you will leave the system. Number of servers, the first service has 3 servers, the second service has 2 servers. Here's the thing that's different in this video is the system capacity. That basically says there can only be 4 customers in the system at once. Let's run a little simulation example to show that this is actually a restriction. So here we've got setting a seed just for reproducibility. And we'll set up a simulation with a tracker that will keep track of the number of customers in the whole system. And then we're going to simulate for 100 units of time. Now from that, just to show from the state tracker the set of different states and how often they occur, we can grab a property or a method of it called the state probabilities, and we'll just print those. And it should be evident from that output, based on the system capacity we set, that there will be 4 of the different states to be in for the whole system population. Okay, so let's give it a run. And there are our, oh, interesting. Is it 0 based? Yeah, no, okay, right. My mistake. The system capacity, of course, doesn't mean that you can't have 0 in the system, which my brain was doing like a computer programmer's 0 indexing going, wait, there's 5 of them, but no, this is fine. You got a maximum of 4, and then you can have different intermediates of 1, 2, 3, and 4, or different intermediates 1, 2, and 3, sorry. And then you can also have 0 in the system. And that's how the system actually started off. So only like 3% of the time was there actually nobody in the system. And 15 or almost 16, let's say, percent of the time, people were in state 1. The system was in state 1, that there was 1 customer. Almost 19% of the time, there were 2 customers in the system. About almost 30% of the time there were 3, and then about, oh, what is that, 0.3, 32%, my rounded percentages probably don't add up nicely, but 32% probability of there being 4. But it may be time dependent. I mean, we could run it longer, for example, to see. This should not change what our maximum capacity is, but this may change the relative frequencies just because of running the system longer, getting a more equilibrated set of numbers. But they're not, they're a little different. What, state 1 was a little bit different than, that's now almost 11%. It was something else a little bit different, but only 3% again of being in 0. Okay. So just to show the other way to make sure that we're a bit convinced that, you know, if I increase the arrival rate, that it wasn't like an arrival rate dependent thing of going, well, maybe that was just 4 was the equilibrium. That no, we should expect that there is a hard maximum being respected here of 4 individuals or customers in the system at once. So you can see with a much higher rate that more of the time, almost 98% of the time, there's 4 of them. But we could just to again keep showing that it really is a constraint that we have control over, set the capacity instead, or capacity as well, and now you can see that there's a maximum of 5, and almost everybody's in the 5th state. And if we set this up to, I don't know what a good number is, but a much bigger number, we might start to see some spread. I don't know how many buckets I want to add before the printout just looks pretty crazy. Okay, we're still seeing pretty much the same kind of effect of almost everyone, or almost all the time, there were nearly the maximum amount, just because we've set the rate here so high. So what ends up happening with the capacity as a fixed number is that you don't get to change it later, and so there are other ways of trying to control the capacity in a dynamic way that are less direct, in terms of controlling things like blocking mechanisms. But this is a good global setting to just simply say, we want to set the maximum. So if for some reason you're simulating a system where it's not the individual nodes, but it's the whole system for some reason, has a maximum number of customers or whatever that are allowed to be in it at once, this is an example way to implement that using the CubePython package. Hopefully that helps you with your simulation project, and I'll catch you in the next video. Have a great day.